All right, here comes the example of our fourth practice problem. You can find all the practice problems on mrras.com, as well as better detail on how to do this in the first place. I'm just kind of answering the problems, but you can get the directions on how to solve these rate law questions in the kinetics section of mrras.com on chemistry. So let's do this one. Let's make sure we can work this one out together. So for reactant A, I want to see when A changes, but the other concentrations do not change. So looking at A, and I see, wow, look at B. It's changing, it's changing, it's changing, and it's changing. B isn't staying very good. So you know what I'm not going to do? I am not going to do A first. I'm going to do B first because B looks problematic. And since it's always changing, there's no constant with B, I need to know what order B is so that I can work with B. So let's do B first. That's why I'm doing B first, because I want to find out what order B is, because B is never constant. So let's find an example where B is changing but nothing else is changing. So an example for that would be I'm looking at 1 and 3. Between 1 and 3. 1 and 3. In this situation here, I see B is doubling and A is staying the same. So between 1 and 3, A is staying the same and C is staying the same. So between experiments 1 and 3, we see that the concentration of B doubles. It's going to be raised to some power. I'm going to say power Y. And what happened to the rate of the reaction? The rate didn't change at all. Well, that's interesting and convenient. So therefore, the rate law, or I'm sorry, the order for B would be a zero order, because if it doubled but the rate of the reaction didn't change, the concentration doubles but the rate of the reaction didn't change, then that would be 2 to what power is 1, and that would be 0. Anything to the 0 power is 1. So this is a zero order reactant for B. In other words, the concentration of B doesn't matter because it doesn't change the rate of the reaction. So that's a really important concept I want you to soak in. The concentration of B does not make a difference in the rate of the reaction, as we just saw here. Therefore, for our other ones, we don't even need to worry about B. B is zero order. Its concentration will not change the rate of this reaction. So let's go back to A now. For A, since B is irrelevant, its concentrations don't change the rate of the reaction, all I got to do is compare it with C. So in 1 and 2, C is staying the same. So let's just do 1 and 2. Between 1 and 2, I can see that A tripled, right? The concentration, so I'm going to say between 1 and 2, the concentration tripled. The concentration's tripling from 25 to 75. And what happened to the concentration here? Well, that's not so easy to determine. So let's see what happened to the concentration here. So I'm going to put 0.756 divided by 0.084, and it went up 9 times faster. So that went up 9 times faster. So as the concentration in A tripled, the rate of the reaction went up 9 times. So 3 to what power is 9? 3 times 3 is 9. So therefore, it's a second order. So A is second order. Okay, let's try C. For C, we're going to definitely need 4, and we want something where A doesn't change. So we're going to use experiment 2 and experiment 4. So I'm going to use 2 and 4 to analyze C. And I see that the concentration from 2 to 4 doubled. The concentration doubled. It's going to be raised to some power. I'm going to say that power is Z. And what happened to the rate? So as this doubled and this stayed the same, and remember B is zero order, so its concentration change doesn't make a difference, doesn't factor into the rate. What happened here? So as that doubled, let's see, I just not able to do that in my head, so let's do 3.024 divided by 0.756. Went up by 4. Went up by 4. So therefore, 2 to what power is 4? The second power. So we have two second order reactants here. Second order. So our rate law would be this. The rate equals K times A squared times B to the 0 power, which is 1, no matter what B is, so we could just leave that out, 1, times C to the second order. Let's rearrange that to solve for K. So K equals the rate over A squared C squared. We're going to pick any one of our experiments and plug in those values to any one of these experiments and plug in the values to see what K equals. So I'm going to choose the fourth one just because we can see it easier on the screen this way. So K equals the rate, which is 3.024. And what's the units for that? That is molarity per second. So I'm going to put molarity per second because that's on the denominator. And in our equation, we're going to put a squared as a denominator. So I'm going to put 0.75 molarity, but it's squared. So let's just put it again, 0.75 molarity. I keep putting those brackets without the unit in there. And then we are also going to have C squared. So that's the 2.4. So 2.4 molarity times 2.4 molarity. I put it twice because it's squared. So these two was because it's 0.75 molarity squared, and these two was because it's 2.4 molarity squared. And I'm just putting it out there so we can see the units canceling, and I can clearly see that I have a second and 1, 2, 3 molarity. And I'm not going to be fancy with my calculator. I'm just going to type it in real simple, safe. So I'm just going to say 3.024 divided by 0.75 divided by 0.75 divided by 2.4 divided by 2.4, and I get this number here, 0.933. So I'm going to put 0.93 because just two significant figures here, so I'm going to use 2. So I'm going to say K equals 0.93, and now don't forget your units. I have 3 molarities that aren't canceled out and a second, so it's on the denominator, so it's per molarity cubed seconds. You need both of these parts for the answer. We need the rate law and we need to know what K equals. All right?